Hi guys, welcome to the next section, using deep neural networks for predictive analytics. Now, we move on to the first video of this section that deals with deep learning for better predictive analytics. Simple machine learning methods that were used in normal-sized data analysis won't be effective anymore and should be substituted by DNN learning methods. Classical machine learning techniques allow researchers to identify groups or clusters of related variables. The accuracy and effectiveness of these methods diminishes for large and high-dimensional datasets, such as whole human genomes. On the other hand, deep learning can make better representations of large-scale datasets to build models to learn these representations very extensively. DL is a branch of ML based on a set of algorithms that attempt to model high-level abstractions in data. Let's take an example. Suppose we want to develop a predictive analytics model, say an animal recognizer, where our system has to recognize whether a given image is a cat or a dog, that is, classification, then cluster dog and cat photos, that is, clustering. If we solve the first problem using typical machine learning problem, we will define features such as if the animal has whiskers or his ears, and so on. In other words, we will define the facial features and will write a method for identifying which features are more important in classifying a particular animal. For the second problem, it is not possible for a classical machine learning algorithm such as k-means to classify images. DL algorithms will take the two problems one step ahead. Using DL algorithm, most important features will be extracted automatically after determining which features are the most important for classification or clustering. In contrast, using a classical machine learning algorithm, we had to manually provide the features. A DL algorithm will first identify the edges that are most relevant to finding cats or dogs. It will then build on this hierarchically to find what combination of shapes and edges exists. After consecutive hierarchical identification of complex concepts and features, it then decides which of these features are responsible for finding the answer. After that, it takes out the label column and do the unsupervised training using autoencoder and does the clustering. Now we will move to artificial neural networks. Let's take a look at the brain's architecture for inspiration, called biological neurons. It is an unusual-looking cell, mostly found in the animal cerebral brain, which consists of cortexes. The cortex itself is composed of a cell body containing the nucleus and most of the cell's complex components, many branching extensions called dendrites, and one very long extension called the axon. Near its extremity, the axon splits off into many branches called telodendrion. And at the top of these branches are minuscule structures called synaptic terminals, which are connected to dendrites of other neurons. Biological neurons receive short electrical impulses called signals from other neurons, then fire their own signals. Based on this whole idea of biological neurons, the term and idea of artificial neurons evolved, including how to build intelligent machines for deep learning-based predictive analytics. This is the key idea that inspired artificial neural networks. Now that we know the ANNs, we need to know about perceptron. The perceptron is one of the simplest DNN architectures, called a linear threshold unit, LTU, inspired by biological neurons. The thing is that the inputs and outputs are now numbers, and each input connection is associated with a weight. The LTU computes a weighted sum of its inputs that can be defined by this equation. A single LTU could be used for simple linear and binary classification. It computes a linear combination of the inputs, and if the result exceeds a threshold, it outputs the positive class or else outputs the negative class. Training an LTU is not an easy job, but training such a simple model means finding the right values. A perceptron is slightly composed of a single layer of LTUs, with each neuron connected to all the inputs. These connections are often represented using special pass-through neurons called input neurons. They just output whatever input they are fed. Moreover, an extra bias feature is generally added. The bias feature is typically represented using a special type of neuron called a bias neuron, which just outputs 1 all the time. Now, let's move on to deep neural networks. Deep learning is a term to differentiate an artificial neural network of multiple hidden layers from the simpler neural network that only consists of a small number of layers. Each layer consists of a certain number of neurons shown as circles, which correspond to certain types of activation functions, such as identity or logistic functions. The connection between neurons is shown by the straight line. DNNs are neural networks consisting of a more complex model with a great number of neurons, hidden layers, and connections. In short, an ANN with 2 or more hidden layers is called a DNN. Now we will see DNN architectures. The basic structure of DNNs consists of an input layer, multiple hidden layers, and an output layer. Once the input data is given to the DNNs, output values are computed sequentially along the layers of the network. At each layer, the input vector comprising the output values of each unit in the layer below is multiplied by the weight vector for each unit in the current layer to produce the weighted sum. Then, a non-linear function, such as a sigmoid, hyperbolic tangent, or rectified linear unit, is applied to the weighted sum to compute the output values of the layer. The computation in each layer transforms the representations in the layer below into slightly more abstract representations. Now, let's see multilayer perceptrons. A multilayer perceptron is a feed-forward neural network, which means that it is the only connection between neurons from different layers. More specifically, an MLP is composed of one input layer, one or more layers of LTUs, called hidden layers, and one final layer of LTUs called the output layer. Every layer except the output layer includes a bias neuron and is connected to the next layer as a fully connected bipartite graph. An MLP was trained successfully using the backpropagation training algorithm for the first time in 1986. During the training phase, for each training instance, the algorithm feeds it to the network and computes the output of every neuron in each consecutive layer. Then it measures the network's output error, and it computes how much each neuron in the last hidden layer contributed to each output neuron's error. It then proceeds to measure how much of these error contributions came from each neuron in the previously hidden layer, and so on, until the algorithm reaches the input layer. This reverse pass efficiently measures the error gradient across all the connection weights in the network by propagating the error gradient backward in the network. More technically, the calculation of the gradient of the cost function for each layer is done by the backpropagation method. There are several known types of the cost function, such as the squared error function and the log likelihood function, and the choice for this cost function can be based on many factors. The gradient descent method optimizes the network's weight by minimizing this cost function, and the steps are weight initialization. Next is calculation of neural networks' predicted output, which is usually called the forwarding propagation step. After that is calculation of cost-loss function. Some common cost-loss functions include the log likelihood function and squared error function. Further is calculation of the gradient of the cost-loss function. For most DNN architecture, the most common method is backpropagation. Next is weight update based on the current weight and the gradient of the cost-loss function. Final step is iteration of steps 2 through 5 until the cost function reaches a certain threshold or after a certain amount of iteration. An illustration of gradient descent can be seen in this figure. There, we see a graph that shows a neural network's cost function based on the network's weight. In the first iteration of gradient descent, we apply the cost function on some random initial weight. With each iteration, we update the weight in direction of the gradient, which corresponds to the arrows in this figure. The weight update is repeated until a certain number of iterations or until the cost function reaches a certain threshold. An MLP is a supervised neural network that is commonly used for classification and regression problems. Although its implementation in image and video data has been gradually replaced by convolutional neural networks. Using MLPs, both the binary and multi-class classification problems can be solved. For multi-class classification task and training, the output layer is typically modified by replacing the individual activation functions by a shared softmax function. The output of each neuron corresponds to the estimated probability of the corresponding class.